Hello everyone and welcome back to another video. And today I kind of just want to mess with this function, this probability distribution right here, this n choose x. So you could also write this as just n choose x right here. But the interesting thing about this distribution, or where it arises, and where I found it at least, is with the Galton board. So if you have like a peg here and a peg here and a peg here, and so on and so forth, almost like a Pascal's triangle sort of thing. The probability that a ball ends up here is given effectively by this distribution, n being the number of rows, x being like the number of peg. But that is outside the scope of this video. And I'll probably do more on that in the future because I am working on a little project there. Sneak peek. That's always fun. Having a lot of fun with it. Shout out to Mr. Winkler, by the way, for actually lending me a Galton board. Anyway, what I want to do in this video is really just calculate how we can normalize this distribution, first off. Secondly, the mean, and thirdly, the standard deviation. So without further ado, let's get started. Just for reference, we are going to be using the discrete version of this distribution. So x is just going to range from every integer from 0 all the way up to n. The integral version is very interesting, but I would like to save that for a video in its own right, because complex analysis is also a lot of fun with it. But I digress too much. Let's just get started. So let's just take a look at some of the sums of this distribution, because again, we kind of want to normalize it. So let's say we're going to sum this from k equals 0 all the way up to n of, n choose k. And one way we can write this again is just k equals 0 to n, of course, but then we have n factorial over k factorial, and then n minus k all factorial. And let's just calculate the, a couple of values. So let's let n equal 0, right? So I should probably make a table. That'd be fun. So n equals 0, right? Okay. When n equals 0, we have a sum from k equals 0 to 0. So we're just plugging in 0 for everything, and we get 0 factorial divided by 0 factorial squared, which is just 1 divided by 1 times 1, which is just going to be 1. Let's plug in 2. So we have the sum then from, k equals 0 to 1 of all that, and I'll just write out the terms, honestly. First, we're going to have 1 factorial divided by 0 factorial, and then times 1 minus 0 factorial, and then plus 1 factorial over 1 factorial, and then 0 factorial. That's just 2. Nothing really interesting here. So 1, that's just 2. It's 1 plus 1. Now let's do 2, right? I swear there's a pattern, all right? And it's more interesting than just, 1, 2, and then like 3, or something like that. So for n equals 2, so n equals 2, we have the sum from k equals 0 all the way up to, 2. And we have, let's plug in everything. I'm actually going to factor out the 2 factorial just for the sake of brevity. We have 1 over k factorial, so 0 factorial, then times 2 factorial, plus 1 over 1 factorial times 1 factorial, because k right there is 1. And then we have the same thing, but kind of swapped on the other side. So we have 2 factorial and then times 0 factorial. This term right here is just going to be 1/2 plus 1 and then plus 1/2 again, because 2 factorial is just 2. And then distributing this 2 right here, we find that this is just 1 plus 2 plus 1, which is 4. Woohoo! And maybe you might start to see a pattern, but let's do one more just to kind of hammer the point home. So what we have now is the sum from k equals 0 all the way up to 3, so we have 3 factorial. And then we're going to have 1 over 3 factorial times 0 factorial plus 1 over 2 factorial times 1 factorial, and then plus 1 over 2 factorial times 1 factorial, and then plus 1 over 3 factorial times 0 factorial. Distributing the 3 factorial, which is just 6, we find that we have 1 plus 3 plus 3 plus 1. And this is just the sum of each line of Pascal's triangle, which is quite interesting. And that right there is just going to be, 8. And you might see a pattern starting to emerge here. The nth term being just 2 to the n. So let's actually test that out, because that seems rather plausible, doesn't it? So dot 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 n, we can have 2 to the n, question mark. So we're going to do this by induction, and we've already done the base case, right? You know, n equals 0 is 1, right? So that's already proven, because 2 to the 0, let me say equals 2 to the 0. So we've done the base case by inductive assumption. I don't want to write all that out, because that would be kind of a waste of our time. We're saying that the sum from k equals 0 to n of n choose k is equal to 2 to the n. So to actually prove this, what we're going to do, going over here, is take the sum from k equals 0 all the way up to n plus 1 now of n plus 1 choose k, and then evaluate this, or evaluate part of it and then, you know, use that. And one thing that we're actually going to do here is find another way to express this right here, this n plus 1 choose k. And according to our recursion formula, our formulae for this, we know that this is equal to, this is according to Wikipedia, n choose k minus 1 plus n choose k. And we have this recursion formula right here, the proof of which I will leave as an exercise to the viewer. But using this, we can see a couple of things, right? So now we have our two individual sums, both from k equals 0 to n plus 1, of n k choose k minus 1, right? And then, you know, plus, there's still a sum, over the same bounds though, of n choose k. N plus 1, of course, and then k equals 0. Now, the interesting thing about the choose function is that because we're dividing by factorials, right? So scrolling up to here, whenever k is, if k is ever greater than n, the function is just 0. And if k is ever less than 0, say like -1, because there's a k factorial here, the entire function, or sorry, the entire term is just going to go to 0. So scrolling down here, why that's relevant is because if we sum from k equals 0 all the way up to n plus 1, well, if we plug in n plus 1 for k, that's just, well, n choose n plus 1, and that right there, because the second number exceeds the first one, well, that right there, and they're both integers, but because the second one exceeds the first one, we're just going to end up with 0, right? So this right here is going to be the exact same thing as before, so this is going to be 2 to the n by our inductive assumption, because we can just kind of drop that last term, so scratch that out. And then, similarly, on the other sum, we see that we're summing from k equals 0, but if k is 0, then we have n choose -1, which is just always going to be 0 for positive n. So what we have is just the same thing again, 2 to the n, and we're adding these two. And that right there is just 2 times 2 to the n, or 2 to the n plus 1. And that right there is what we would expect to get. We have the next term in our sequence. Thus, that right there is our formula. So, since the sum of all of our points in this distribution is in fact equal to 2 to the n, the one way we can actually normalize this distribution is just by adding this term of 2 to the minus n out front. And now our distribution is normalized, and our sum our sum of everything is just going to be 1. But now let's go calculate the mean. To find the mean of this now normalized distribution, what we can do is effectively sum over it, but weigh each point along the way. So what I mean when I say that is effectively evaluating this following sum. 2 to the minus n times the sum from k equals 0 all the way to n of n choose k. But we're going to add in an additional k here to effectively weigh each point. And to evaluate this right here, it really isn't too awful. We were going to have a 2 to the minus n out front. We'll deal with that at the end. But now we have this sum right here. So I always want to write infinity. It's kind of funny. But now we have n factorial times k over k factorial, and then n minus k all factorial. And to evaluate this, we can exploit a couple of things. Namely that k factorial, this right here, is equal to k times k minus 1 factorial. So we can actually cancel these k's right here, which leaves us with the following. So this sum, I'm going to put the n factorial, actually no, I won't. I changed my mind. N factorial right here. And then we have a k minus 1 factorial in the denominator. But then we also have an n minus k factorial. And this doesn't look very nice to deal with, in all honesty. But we can we can manipulate this in a couple ways to make it very doable. And that right there is to adjust, in a way, what this n is. And what I mean when I say that is that we can actually just factor out an n from the entirety of the sum, right? So erasing this, we can stick an n out front, and by properties of factorial, say this is n minus 1 all factorial. And then if we look down to this n minus k term, we can actually expand that a little bit, can't we? Instead of just n, we can say this is n minus 1 factorial, or not factorial, just n minus 1, and then minus k minus 1 all factorial. And you'll see here that the ones will just cancel, and what we're left with here, what this is right here, is just n minus 1, choose k minus 1. And we're summing over that, so we have k equals 0 to n, and then we have our stuff out front. But we effectively know what this is, because if it were just n and k in the choose function right here, then the answer right here would just be the inverse of our normalization constant right here. It would just be 2 to the n. We already figured that out. But since it's n minus 1 here, and we're summing from k equals 0 to n, what it's going to be is 2 to the n minus 1 right here. And that right there is going to be multiplied by everything out front here. So we have an n times 2 to the minus n. And what we see here is that, well, half of this cancels, the 2 to the minus n and the 2 to the n, and this just leaves us with an n over 2. And that right there is the mean of our distribution. So, without further ado, let's go on to the variance and standard deviation. The standard deviation for this distribution can be found by the following. So we're going to have 2 to the minus n out front. Then we're going to have our sum from k equals 0 to I keep wanting to say infinity, my goodness. I'm too used to doing infinite sums. Sum from k equals 0 to n of, well, n choose k, of course. So n choose k. But then, as the formula for variance, it's really variance, goes, to find the standard deviation, we're just going to take the square root of all this in the end. But to find the variance, we're going to have a k minus n over 2 all squared. And the reason why we have that is because, well, we have a weighting thing right here at k, but then we have to subtract that from the mean. So it's how far, what's like the average distance from the mean. Because that's what, variance and standard deviation are. It's what they measure. So to evaluate this, what we're actually going to do is really just expand everything and see what we get from there. So I'm gonna just bring down this like 2 to the n term the whole time, because that's not really our main concern. But what is our main concern is this n factorial over k factorial, and then times n minus k factorial, and then times k squared, plus n squared over 4, and then just minus kn. And let's just go left to right evaluating each one of these. So for our first one, for our k squared, we have the sum from k equals 0 to n still. N factorial is out front. Actually, I'll keep it in the sum just for the sake of that. N factorial over k factorial. And then we have a k squared, and then our n minus k factorial. And the way we're going to take care of this is actually a little bit fun. I liked it, at least. What we're going to do is start off what we did when we were finding the mean of our distribution. And that is to cancel a couple things out. So we're going to have, or cancel a term out of the factorial with one of the squareds. So we're going to have the sum for k equals 0 to n still of n minus 1 factorial, and then we have our extra k here, but then we have k minus 1 factorial, and then we have our n minus 1 minus k minus 1 all factorial. But the way we can take care of this is by adding 1 and subtracting 1 to our k. So minus 1 and then plus 1, extending the fraction bar. And whenever we distribute, the rest of this fraction, this right here, once we distribute that to this k minus 1, treating that as one term, and the plus 1, we can actually evaluate this. So what we end up getting is our sum. I'm not going to bother writing the bounds. It's the same. We have n minus 1 factorial, and then we have over k minus 2 factorial, because we can factor out k minus 1 from this factorial. K minus 2 factorial. And then we can do something similar with this term right here. We can just say this is n minus 2 minus k minus 2. So I have n minus 2 minus k minus 2 factorial. And then we can also factor out an extra term in the numerator, right? So now this is, there should be an extra n out front. I do apologize. Now we have an n times n minus 1 times n minus 2 factorial. And we know exactly what this sum right here is. This right here is just going to be, well, 2 to the n, but then minus 2, because, well, it's just n minus 2 right here. Another way you could actually think about it is you re-index the series, and you get it that way, but I'll leave that to you to do on your own time, I guess. So now we have n minus 1, 2 to the n minus 2. But we can't forget about this extra plus 1 right here. So let's think about what that is right there. So we have a plus. I'll keep doing this like the yellow. Still our sum. N times n minus 1 factorial divided by, well, k minus 1 factorial, and then n minus 1 minus k minus 1 all factorial. But this right here is just going to be, well, plus n times 2 to the n minus 1, because we already evaluated the sum for our mean. So this right here is roughly half of what we need for finding the variance. Going on to the next term, we're just going to collect our find all of our terms and then kind of smush them together at the end, and we'll see what we get. The next term is actually relatively easy, because you'll see that this is an n squared over 4. Nothing here actually depends on k. So because of that right here, this sum is just going to be n squared over 4, and then times just 2 to the n, because, well, that's the total of the distribution. So yay, that was simple. Moving on to the next one. The worst one is already out of the way. Moving on to this one, we have just minus n times k, or I'll actually write out the whole thing. So sum, and then k, and then n choose k. But didn't we already evaluate that? Like, yeah, we already did. This is just our mean. So this right here is literally just minus n times 2 to the n minus 1. So with all of this in mind, let us combine all of our terms. I do apologize. There's an extra 2 right here. That is n squared, because our mean is n times 2 to the n minus 1, and we already have an additional n out here. So it's minus n times 2 to the n minus 1. Now to combine all of our terms. And this right here is the collection of all of our terms. So to find our variance, we're just going to have to evaluate all this and then apply our normalization constant that's up front. But the first thing we're going to do is just distribute this right here to get everything in terms of n and n squared. So we have n squared, 2 to the n minus 1, and then just kind of grouping everything, getting all of our n squareds in one place. We're going to have plus n squared over 4 times 2 to the n, and then we're going to have a minus n squared 2 to the n minus 1. And then we have plus 2 to the n minus 1, just this term right here. And then we have this extra term right here with the minus 1. So then minus n 2 to the n minus 2. And here's the really interesting part. It looks like this doesn't simplify too much, but let's take a very close look at this right here. What we have is a bunch of 2 to the n's, or an n minus 2. So let's get everything just to a common base to make things simpler. So factoring out n squared, we have 2 to the n minus 2. That part doesn't change. But then here we have a plus 2 to the n minus 2. Because, well, we have a 4, and by properties of exponents, that becomes a, minus 2. And then we have a minus, 2 to the 2 times 2 to the n minus 2. Again, just by properties of exponents. And you'll see that this all just cancels. This right here is just 0, because, well, this right here is just 2 times 2 to the n minus 2, or 2 to the n minus 1. So since that right there is 0, what we're left with is just this right here, this bit right here, and that right there isn't too awful either. We just have an n times 2 to the n minus 1, and then minus a 2 to the n minus 2. But we can kind of bring 2 from the exponent and say this is 1/2 2 to the n minus 1. And what we get then is n over 2 times 2 to the n minus 1. But what was our normalization constant out front? Well, outside of all this, we had 2 to the minus n. So, throwing that back in, what we find is that this 2 to the n actually just cancels. And what we're left with for our variance squared is equal to n over 4. Or, if you want the standard deviation, this right here is just going to be the square root of n over 2. So I hope you all enjoyed this video on the mean, standard deviation, and also normalizing this fun little distribution, the choose function. I'll probably do another video on it in the future, but involving integrals and or expanding on it with skew and kurtosis, because I have a feeling my project will go that way. But whatever the case, I'll keep you all updated, and it'll be a lot of fun. So thank you for watching again, and I'll see you in the next one.